welcome to kinematics in 2 dimensions. We are going to be talking about something called projectile motion today. And for most of you, projectile motion will be pretty exciting, other than the math part, because this is when you launch things in the air. So this is a picture of a catapult, and a catapult is all about projectile motion. So what is projectile motion? Well, a projectile is an object moving in 2 dimensions under the influence of the Earth's gravity. So the 2 dimensions, if we look at this ball being dropped, the 2 dimensions it's moving in is to the side and down. It is moving over and down at the same time. So when we add these 2 vectors together, we get a resultant like this. This is our resultant here. And then if we wanted to add after that, we would have to do the x and y components of each part from there to get the resultant. When you look at the motion of a projectile overall, it forms something called a parabola, and that is this thing right here. Parabolic motion. A parabola is a mathematical function, and all projectiles follow this function and will make this shape as they're traveling. So we can understand projectile motion by analyzing both horizontal and vertical motions and doing it separately. So for this ball, let's say it's a ping pong ball that rolls off the edge of a table. It is going to fall in the shape of a parabola. Automatically. It does that naturally. What we need to do to look at and analyze this ball's motion is we need to look at its x, or horizontal motion, and its y, or vertical motion. The horizontal motion for the ball at each part looks like this. Hopefully, you notice that the vectors in the horizontal position are always pointing to the right, which means it's not changing direction, and they're all the same length. So this picture tells us that this object is not speeding up or slowing down while it's falling in reference to the horizontal position. However, if we look at our y positions, the vertical vectors get longer and longer, and that's because as this ball falls, it is falling because of gravity. Gravity is pulling it down. And remember, we always have an acceleration due to gravity of negative 9.8 meters per second squared. So as this ball falls, it keeps speeding up in the y direction. It speeds up as it goes down, but it does not speed up in the horizontal direction. And if you notice, this picture right here is really just vector addition. We have our x component and our y component, and we can add it to get the overall vector, or the trajectory. Here, trajectory means path of the ball. So the yellow arrows are our horizontal components, the purple arrows are the vertical components, and the blue arrows are the overall trajectories of this ball. So the speed in the x direction is constant. It does not change. In the y direction, the object moves with a constant acceleration of g. So this photograph right here shows us 2 balls that start to fall at the same time. The one on the right, or the red ball, no, the yellow ball, sorry. The one on the right has an initial speed in the x direction. So it's being pushed out. And it can be seen that even though this yellow ball has an initial speed in the x direction, it does not have an effect on the speed in the y direction. In the y direction, both of these balls have an initial velocity of 0. So even though the yellow ball moves to the side, whereas the red ball moves straight down, both of these balls are going to be in the same vertical position every time, because the only thing making them fall is gravity. And remember, the acceleration due to gravity is the same for every object. The only thing that would change these two balls being in different positions at the same time is if one of them had an initial y velocity. So it was thrown up in the air or thrown down, not just dropped. So we can see by this picture a really, really crucial point of projectile motion, that x and y are separate. If you try and solve projectile motion problems with the x and the y's mixed up, or trying to solve them together in the same kinds of equations, you are doomed to fail. Always, always, always keep x and y separate. If we have an object that's launched at an initial angle, like this guy, the analysis is similar, except now it has an initial velocity in the y as well as in the x. So here our vector addition will come in handy, because we have our resultant vector, which is the path the ball takes, and we break it down into x velocity and y velocity. And from there, we can analyze the motion in the x and the motion in the y separately. So projectile motion is motion with a constant acceleration in 2 dimensions, where the acceleration in the vertical dimension is g and down. Always, always, always. And the acceleration in the horizontal dimension is 0. Always, always, always. So the final and initial horizontal components of velocity will always be the same. So this is the key. Like I said before, you have to take the motion in the y and the motion in the x and keep them independent. You can't cross-mix them. It doesn't work. So let's try our first problem, and I'll show you what I mean by keeping them separate. This is an example of an object launched horizontally off a building. A ball is thrown horizontally off of a 100-meter building with an initial velocity of 20 meters per second. How far away from the building does the ball land? These problems are still constant acceleration problems, so we follow the same exact steps we did for constant acceleration in 1 dimension. The only thing that's different here is now we have an x and a y. So to start, the very first thing we're going to do is draw a picture. So we have a building, and we have a ball, and it's being thrown horizontally. So we know the ball is moving over and not up and down. This building is 100 meters tall. And we know that this initial velocity is equal to 20 meters per second. But what kind of initial velocity is this? Is it in the x or is it in the y? Well, it's being thrown horizontally, which means to the side, so this is the initial velocity in the x. But what is the initial velocity in the y? Do we know this? We do, in fact, know what this is. The ball is being only thrown to the side, not up and down, so the initial velocity here is 0. So once you have drawn a picture and labeled a few things, the next step is to make a chart of what you know and what you don't know. The only thing that's different about this now is that we are going to have 2 different columns for our chart. We are going to have an x column and a y column. We still have all the same variables that we had before. We have final velocity, initial velocity, acceleration, time, initial position, and final position. But now it's going to be different for the x and the y. And this is what I mean by keeping them separate. So let's go through and just add some of the things we know. We know that the initial position in the y here is 100 meters. And we know it's in the y because this is an up and down displacement, not side to side. And if its initial position is 100 meters, that means its final position in the y must be 0 because it's going to land on the ground. We know the acceleration in the y direction. It's negative 9.8 meters per second squared. The reason this ball falls from 100 meters down to the ground is because gravity is pulling on it. And gravity always has this acceleration for any object ever. We know from looking at our picture that the initial velocity is 0 meters per second in the y. And do we know the final velocity in the y? We do not. Do we care? Well, this question is asking us how far away from the building does the ball land? So this phrase right here, how far away, tells you we are looking for a displacement. So we do not care about this, about the final velocity in the y. It does not matter to us. We don't care. Now let's go back and let's fill in some of our x here. The initial position in the x, we can call this point 0. We are arbitrarily saying from the edge of the building, it's 0. Do we know how far away it lands? Well, it's going to take the trajectory of a parabola. And do we know how far away it is? No. Do we care? Yes. This is what we're solving for right here. The final position in the x of the ball. How far away from the building does it land? So if this is our building here, the displacement we're looking at is a horizontal displacement. We know the acceleration of this ball in the x. Do you think the ball speeds up or slows down while it's moving to side? No. The acceleration in the horizontal direction is always, always, always 0. That makes it easy for us when we think about the initial and final velocities. We know the ball is thrown with an initial velocity of 20 meters per second. And if its acceleration is 0, which means it doesn't speed up or slow down or change direction, our final velocity also has to be 0. Final and initial velocities in the horizontal direction are always the same. So the one thing we have left here is the time it takes for it to fall. And let's think about this for a second. Is the time it takes to go from 100 meters up here to 0 going to be different from the time it takes to go from the edge of the building to its landing point? No. These times are going to be exactly the same. Time cannot be split up into x and y components. Time just is. So this time is going to be the same for your x and your y. Always. So now we can look at what we have and try and figure this out. We are going to use one of our 4 constant acceleration equations. The problem is, you're probably looking at this and saying, okay, we need to solve for final position in the x, so we're going to pick something that has that and then fill it in. Problem is we can't do that. Only because the only information we have about the ball in the x direction is that it's not accelerating. So if you try and use just what you have in the x column here and plug it into an equation and solve, you're not going to get anywhere. It's going to be totally useless. So what we need to do to solve here is we actually need to find the time it takes to fall and then use that time to solve for how far it goes. So this is a 2-step problem, and the majority of your projectile motion problems are going to be 2-step problems. So what we need to do is find an equation and use what we know in the y to solve for t. And remember, we do not know, nor do we care about the final velocity in the y direction. So we need an equation that does not have final velocity in it. And that's pretty easy. We use this one a lot. It's the very first equation. Change in position is equal to initial velocity times time plus 1/2 acceleration times time squared. And now we need to plug numbers in. But remember, all of these are numbers for the y direction only. So change in the direction in the y times initial velocity in the y times time in the y, which is the same as time in the x, so we don't need to label that one, plus 1/2 acceleration in the y times time squared. So the change in position in the x is in the y, is 100 meters. It falls from a height of 100 meters down to 0. So its displacement is negative. It starts at a high number, falls to a low number, and it falls 100 meters. So negative 100 meters is equal to the initial velocity in the y times t, which is 0 times t, plus 1/2 negative 9.8 meters per second squared, which is our acceleration in the y, times t squared. So we have negative 100 meters is equal to negative 4.9, which is 1/2 of negative 9.8, t squared. Divide both sides by negative 4.9 to cancel it over here. Get my calculator. Negative 100 divided by negative 4.9 is 20.4, which is equal to t squared. And the final step is to take the square root. Square root both sides, and t is equal to, all right, square root of 20.4 is 4.5, and the units for time are seconds. Are we done here? Sadly, no. We have solved for the time it takes for this ball to fall from the top of the building to the bottom. It takes 4.5 seconds to fall. However, that's not what we were trying to look for. It's not what this problem is asking us for. It's asking for how far away from the building it lands, which is the final position in the x. So now that we have the time it takes to fall, we can finally use our x column. We can use that information to solve for its final position. We know everything there is to know about the x, so we don't have to worry about picking an equation that has something left out of it. However, we do need to make sure we have an equation that has x in it, because that is what we're solving for. So I'm going to go ahead and use this equation. The very first one. Change in position is initial velocity times time plus 1/2 acceleration times time squared. And remember, we are now looking at all of this information in the x, in the horizontal direction. So the change in position in the x times initial velocity in the x times t plus 1/2 acceleration in the x times t squared. Now we can go ahead and start plugging numbers in. We do not know the change in position. That's what we're trying to look for. We do know the initial velocity, 20 meters per second, and we do know the time it takes. We just solved for that, 4.5 seconds. Plus 1/2, 0, 4.5 squared. So we can simplify this to the change in position in the x is equal to 20 times 4.5, 90 meters. And because we said the initial position in the x is 0, that means the final position in the x, or just x, is going to be 90 meters away from that, or 90. So this is your answer. These problems are pretty long. They take a lot of thought and a lot of time, But if you walk through the steps of drawing a picture and then writing down what you know and what you don't know, and choosing an equation, you'll be fine. Just remember, if you are not given the time it takes for an object to fall or launch or whatever the problem is, you need to solve for time in like 90% of these problems. So solving for time is your first step. And once you know how long it takes, you can then use that information to solve for whatever your unknown is. So your homework is to answer this one question, and you will need to follow many of the same steps that I did in the previous problem. So use this one as a reference for this problem. A soccer ball is kicked horizontally off a 22-meter high hill and lands a distance of 35 meters from the edge of the hill. A, draw a picture, and I will take points off if you do not have a picture. 2, which should be B, make a chart of your knowns and unknowns for both the X and the Y, and I will take points off if you do not have this completed. And 3, which should be C, determine the initial horizontal velocity of the ball. So work on this, do the best you can, and be ready to hand it in when you come into class.